Hi guys, welcome back to the channel. Hope y'all are doing well. Today we're going to talk about database indexes and how it applies to relational databases. You can see a table of contents over here. This is what we're going to cover in the video. At first, I'm going to talk about what an index is. We are going to build some example tables with some example indexes, and I'm going to walk you through how, given your query, the database engine is going to decide to use the index. Once you get an idea about the basics, we are going to dive a little bit deeper into how the database engine actually decides whether to use an index or not. We're going to talk about compound indexes. These are essentially indexes on multiple columns at once. After that, we're going to take a look behind the scene to see what kind of data structure is actually created to maintain and update the different indexes you create. Finally, we're going to wrap up the video by talking about a few downside of indexes, which is going to explain to you why creating an index is not always a good solution. Okay, so with that being said, let's get started with what an index actually is. All right, so let's say we have a relational database and a table in it called books. This table contains all the books in our library. So we have a query over here. It's a very simple query. We are essentially looking at our books table and selecting the row with title set to silent patient. In a world where we do not have an index, the database is going to scan every row of the books table until a match has been found, right? So if we have 1 million books in our table, the database is going to go and scan all the 1 million rows until it finds a book with the title Silent Patient. For a small table, this can work just fine, but for larger tables, this can be very expensive. So if you have tables that have a few thousand rows or a few 100,000 rows, doing a full scan of the whole table to find one row can get very expensive. Now, what's the solution? So we, of course, don't want to scan all the rows given it's going to take longer. So the solution is going to be to create an index on the title column, right? So we have multiple columns in our table, but we know that in this query, we are searching the table by the column title. So we can go ahead and create an index on the title column. Now let's talk about what does this actually mean. So when I say creating an index, what does it mean? So an index is similar to a book index or a phone directory. If you remember, in a phone directory, if you are looking for anyone's phone number, you don't go to the directory and search from the first to the last. You skip over until you find the section where alphabetically the names are starting with what you are looking for. To give an example, if you're looking for Max's number, M-A-X Max, instead of going to your phone directory and searching for Max from the first to the last entry, you're going to skip over every contact that does not start with M. And then once you find the contacts that are starting with M, you're going to start looking for Max. So a database index is very similar. When you create an index on the title column, what the database is going to do is organize all the title values alphabetically. Okay? And then it's going to map every title to the disk location where the full row resides. And it's going to store this mapping in a separate storage. So what's essentially happening is when you're creating an index on the title column, your database looks at all the different title values that are there in your database. It organizes them or sorts them alphabetically. And then for every title value, it creates a pointer to the disk location where the full row actually exists. And this whole mapping or this whole index is being stored in a separate storage. Okay, so if we skip around a bit and look at this example index, the data structure that the database is creating to maintain the index is very similar to the table you see here. As I talked about, we are creating the index on the title column. So this is how your database is actually gonna create the index. So I'm gonna create this in an alphabetical order to make more sense of it. So let's say we have atomic habits, and then we have sapiens, and then we have silent patient. Okay, so you can see we have 3 rows over here, and it's alphabetically ordered. For every row, so for every title, we have the memory location. So this is the memory location of the row in disk, right? So this is the memory location or disk location, whatever you want to call it. But essentially, this is a pointer for a row that has the title Atomic Habits. Okay, so this way, when you want to find a row with the title set to silent patient, instead of scanning all of it, you can go to the index, you can go to the location where the entries are starting with S, and then you can go to silent patient, find the memory location, and then actually go to the disk and fetch the row for silent patient. Okay, so how does a search with index work? It's exactly how I explained. The title values in your index are organized alphabetically. Let's say you're looking for silent patient. You check the index. You skip over all the rows before S. So in this case, you skip over atomic habits. You scan a small proportion before finding silent patient. So if you're looking only at the first letter, you skip atomic habits. You go to sapiens. So this is an entry with S. And then you start scanning sequentially until you hit silent patient. Okay, so this is much quicker to do it this way rather than do a full table scan for every single book on the table. Okay, so now we have an idea how the index looks like. Let's talk about a different table now. Okay, let's say we have a table with 4 columns: ID, name, age, and gender. You can see that we have ID 1, name John, age 12, gender male, and then we have 2, Sarah, 15, and female. By default, most database engines, they are gonna create an index for you based on the primary key of the table. So in this case, our ID column is the primary key. So the table is already gonna create an index for you for that ID column. Now, if you have a query, example would be select star from students where ID equals 2. So we're calling this table students, and we want to find the row where ID is set to 2. Now, your table, instead of scanning every single row until it finds one with ID equals 2, it's just going to use the index on ID and very quickly give you the row. This is something you get by default. Most database engines, they are already going to create an index on the primary key, which in this case is going to be the ID column. Now let's look at another query. Select star from students where name equals John. Now, of course, we don't have an index on the name column, so you do need to scan every single row until you find one with name equals John. Once again, this can get very expensive for large tables, so a solution would be to create a new index on the column called name. Now, when you execute the same query, you can just look up the row location for John using the index and go straight to the row's location on disk. So I am switching between memory location and disk location. Essentially, this is a pointer to the location of the row. Okay, so in the most basic terms, that's how an index works. It makes lookup queries very easy if you are indexing the correct column. So now let's talk about a little bit more complex use cases. Let's say now your query is as such. You have select star from students where name equals Sarah and age equals 15. Let's say you have two indexes in your table. One index is on age, another index is on name. Okay, so we have two rows, name and age, and we have two separate indexes on both of these. Okay. So the question is, now that in your where clause you have name equals Sarah and age equals to 15, so you are querying by two columns at the same time, will the database use both of your indexes at once? The answer to that is most probably no. Typically, databases use only one index to query the table just for performance reasons. So in this case, your database, it's going to look at the index name because that's the first thing you're querying by. And it's going to see that there's only one row in the table with the name equals Sarah. In that case, it can just directly go to disk after it talked to the one index and get the row with the age set to 15. Okay. Now you might ask, what if we have multiple rows of Sarah? So maybe Sarah age 15, and then we have Sarah age 20, Sarah age 25, multiple of them. What your database can do is go to the first Sarah and then do a sequential scan until it finds a Sarah whose age is 15. It's much more efficient this way than consulting two separate indexes. And databases, for a lot of cases, even if you have two indexes, it's going to end up using one to get better performance. So that's how databases can decide against using multiple indexes at once. However, you can have something like a compound index, right? Compound index is very different from having separate indexes for individual tables. For compound index, you can have one index based on multiple columns. In this case, let's say you are creating a compound index on the combination of name and age. And we're going to make the assumption that in your database or in your table, you have many rows where the name is Sarah. So you have many Sarahs in your table. Now let's talk about the same query. You want to find Sarah whose age is 15. Unlike the last time, where we knew that there were only a handful of Sarah in our database table, now we have many different Sarah. So instead of using only the name index, so only this index, we are going to be using our compound index, which is going to be name and age. Okay. And now, instead of going to the first Sarah and sequentially scanning all the rows until you find Sarah with age 15, we are going to use the index to find all Sarahs whose age are 15 and then go and fetch them from the disk. Okay, so this way we are avoiding doing a sequential scan on all the Sarahs in our database. Instead, we know exactly where Sarah whose age is 15 resides in our database. We consult the index, find that row, and then bring it back to the user. Now, one cool thing about compound indexes, it can be used both as a compound index and a single index. To give you an idea, let's say if your query was something like this, where name equals Sarah, so you're only querying by name, you can still use the compound index. Even though your index is set on the combination of name and age, for queries where you're doing name equals Sarah, you can still use the index. And of course, if your query is something like name equals Sarah and age equals 15, this is the example we talked about before. We can go ahead and use the compound index because the index is organized by name and age. However, one subtle difference is if in your query you have something like age equals 15 and name equals Sarah, so you have the age at first and the name second, you cannot use the compound index, name, and age. That is because the order matters. In your query, you have age at first and then name. However, in your compound index, you have name at first, age second. Because the orders are different, you cannot use the compound index or this compound index for the query above. Okay. You would have to refactor the where clause to have name first. So you would have to do where name equals Sarah and age equals 15. The order of columns in the where clause will need to be the same order as your compound index. Otherwise, if you keep this query as is, your database will look for an index age, right? So remember, we did have an index on age. Your database engine, it's going to look at the first column of the where clause, which is age, and then look for an index that is either on age or starts with age. Okay, so that is a subtle difference between different times that the database engine can either decide against or for using an index. And you want to keep in mind that the order over here matters when it comes to whether the database is going to use an index or not. Okay, so now let's talk about a little bit behind the scene and what actually happens when you create an index. For every index you create, your database creates a B tree, which is a data structure, which is very easily sortable. As mentioned, B trees are easily sortable, and it's also very easy to search for something. When I say that the database is creating a B tree for every new index, it is not actually storing your whole row in the B tree. Instead, when you create an index in the B tree, the database is inserting the column of the index. So if you're indexing on the column title or on the column age, in your B tree, the only piece of data that's going to be there is this column value. So whether the age value or the title value. With that value, in every node of the B tree, you are going to store a pointer to the actual location of the row in disk. So let's say if you have age equals 15, right? Now your database or your B tree, it's going to store that 15, that value 15, and then a pointer to the row where the full row with age 15 is. Okay. That way, even though you can create multiple indexes, your space, the amount of space you're using is not going to be exactly the same space as the database. It's going to be very little because you're storing the value and the pointer only. Okay, so we're going to wrap it up by talking about some of the downsides of indexes, because it might look like the only solution to optimize your queries is going to be adding newer and newer indexes. However, that's not really a good practice, and you want to be mindful about when adding any new indexes. The first thing is you do use memory when creating index. Every time you create an index, in the backend, you are creating a B tree with the value of the index and the value of the indexed column and the memory locations associated with it. So the more indexes you create, the more B trees need to be built, so more memory is being consumed. Also, every single time you create an index, or the more indexes you have, your insert, update, and delete operations can get very slow. This is because whenever you are inserting new data, updating old data, or deleting data, your index needs to be updated too. So the more data you write or update, the more your indexes need to change. Hence, the operation can get slower and slower. As talked about, in some cases, you will have to rewrite the whole B tree and rebuild the whole index, which is expensive. So not only do you have to update the index every single time you're writing some new data, in some cases where the index needs to be shaped quite a bit, you're gonna essentially rewrite the whole B tree or rebuild the whole index. And this can be a very expensive process. So a few things to keep in mind when you are deciding what columns to index on. If your column is changing too much, don't index it. So if you have a table where you have a certain column that keeps changing depending on your application needs, don't index that column, because every single time you update the values in that column, your database will have to go tweak or even rebuild the index, which can be very expensive. If you do bulk writes, reconsider indexing, right? So if you have a use case where you have some kind of a batch job that does a bulk write, so let's say it writes a few 100,000 or a few million rows at once, make sure you don't have too many indexes, because every time you are doing this bulk operation, if you have too many indexes, all of them would need to be updated, which can make the whole write process very, very slow. Lastly, if your column has too many null values, indexing might not give you a performance boost, so reconsider indexing in that case. Finally, indexing is not always the solution. If you have a small table, you don't really benefit much from index, because when you have an index, you do have the overhead of not only storing the index in memory, but also going to the index, looking up the information, which does take some time. So if you have a small table, you are better off just doing a sequential scan to find your row rather than using and maintaining multiple different indexes. Okay, so I think that's all I had for you folks today. Hopefully that was helpful. I do have all the resources linked here. Please go and check them out if you want more information about how it works. I am gonna go ahead and turn this into a PDF and put it in the description below for you to take a look at. With that being said, if you have any questions, please put them in the comments below, and I'm gonna try to get back to you as soon as I can. And yeah, I'm gonna catch you in the next one. Bye-bye.